our notes are over linear approximations. So I'm just going to reread what the linear approximation is. It's the use of the tangent line at a point as an approximation to the curve y equals f of x when x is near a. So I'm trying to find an approximation of what f of some x value would be by using what it's close to. And so on example 1, we have our function, and we're wanting to approximate, we're wanting to find an approximation for f of 2.97. So we know 2.97 is close to 3, so we found the tangent line for when x is equal to 3. So here was all our work to find that. And then once we found our tangent line, we then plugged in 2.97 to find that f of 2.97 will be approximately 13.580. So now in our calculator, I'm going to kind of go through all of that process too. So I typed the function in to y1. Currently though, on the normal settings, I cannot see where 113.580 is. So I'm going to go change my window to where I can see it. My x values are fine. I just need to go, I'm going to change this to 0, let's say 125, counting by 25. And then now, now we can see somewhere up here is that f of, here's 1, 2, so f of 2.97 is like right here. So about 113 should be right there. Okay, so now I want to look at two things. I want to look at the tangent line right there. So the tangent line, we solved it for y, and it was 114 times x minus 3 plus 117. So now we see that tangent line. So right here, 1, 2, 3, if I just go straight up, do you see how close that intersection is to the same value as what f of 2.97 is? So that's why, and it's really, see how the tangent line, it touches at x equals 3, but it's also really, really close to what f of 2.97 would also equal. And so one more thing I'm going to look at, how close did we get to finding f of 2.97? So we said it was 113.580. So now if I go tell my table to look right at 2.97, see how close my answers are? The correct answer is 113.61. So the linear approximation, we did all that without even using the graph. We had big numbers, so we did calculate them. But the process of finding the equation of the tangent line allows you to find other values. So in general, the process for using a linear approximation would use these two formulas. Okay, so find equation of tangent line at A, where A is near X, what we're trying to find of. So I could say using linear approximation process to find f of x. And so now I'm going to pick some value that's near a, and I'm going to write that equation with that tangent line. So I know I'd have my point a, f of a, when I write my equation of my tangent line. And then I would need my slope, f prime of a. So my tangent line would be y minus f of a equal to f prime of a times x minus a. And then now to get my linear approximation, my answer, I guess you could say, we would solve for y. Solve for y from above, which would give us y equals, and it's an approximation, so I'm going to change that to a swivel. We would add over f of a, so f prime of a times x minus a plus f of a, and then we would just change y to f of x, and that's where we would plug in whatever x was. Right here and right here. And so that's how I find f of some value using the tangent line.
So that's just what we did yesterday, put in weird letters.
Yes, and we'll do one more example. We can also describe our approximation as being high or low, and we use that tangent line to describe it. So in our example, is the approximation high or low? And how do we know it's low? Good. And we use, where was the tangent line? And if I don't know if y'all saw when I graphed it, it was concave up, increasing. The function was, so the tangent line was below it. So it is low. Good, I'm glad y'all knew that. Low, because the tangent line is below the curve at x equals a.
So will this test be calculator, or are we not going to do something like that? We need to see the tangent line.
I think part of the test is calculator.
Okay.
Let me double check. Yes, this entire test you may use a calculator on it.
What did you guys
Okay, so example number 2. That's kind of lengthy. Alright, the only information we have about a function is that f of 4 equals -2. And the graph is shown. So we're going to draw the graph of the derivative. I'm just going to go out to 8 on my x. Negative 2 on my x-axis, negative 3 on my y. We have a y-intercept at 4. 1, 2, 3, 4. We have a 0 just a hair past negative 1. And another 0, 1, 2, 3, 4, 5, 6, just a little past 6, looks to be in between 6 and 7. And I have an exact point at 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 4, 6. This is point 4, 6. And it is a parabola going through those points. Linear approximation to estimate f of 3.9. And then is your estimate high or low? Okay, so if I'm finding a linear approximation of f of 3.9, I need to find some value that's close to it and write the tangent line at that value. So what value is close to it? 4. So I'm going to write equation of tangent line for x equals 4. So my point, they gave it to me. When x is 4, f of 4 equals negative 2, so I have the point 4, negative 2. And what is my slope at f prime of 4? They gave me the graph of the derivative, and so my slope is 6. So we can write our equation of our tangent line, y plus 2 equals 6 times x minus 4. So now I can solve it for y by subtracting 2 over, or writing it as f of x equals 6 times x minus 4 minus 2, and now I can plug in my value, which is 3.9. So f of 3.9 would equal 6 times 3.9 minus 4 minus 2. Okay, what does that equal? Or it's an approximation. If you have your calculator out, you can type it in. 6 times 3.9 minus 4 minus 2. 1.4? Negative 2.6. So f of 3.9 equals approximately negative 2.6. So we answered the first part. Now we've got to figure out, is it high or low? High. And why do we say it's high?
The tangent line would go above the parabola.
function would be concave down at x equals 4. And we could, so let's do our sign analysis of the function and its derivative. I know I have zeros at negative, let's say 1, we'll just approximate, and 6.5. To the left of -1, it's below. In between, it's above, and then to the right, it's below. Which means the function is decreasing, increasing, and then decreasing. 4 is going to be somewhere in here. So I'm decreasing, and then I'm increasing, and then I'm decreasing again.
So it'd be high?
So it would be high. And you could even kind of sketch that out. So I have a minimum at -1. We don't know where, but it's decreasing, and then it's going to increase. So here's 6. That's a maximal. And then it's decreasing. So at 4, it is concave down. Y'all see that now? Which means the tangent line would be above it. And so it is a high approximation. So high tangent line is above at x equals 4. I'm going to go ahead and introduce topic 27 since I'm not going to be here tomorrow. Tomorrow in class, work on homework assignments. That's all you'll do in class tomorrow. So topic 27. We're looking at derivative of trig, piecewise, and absolute value functions. I'm going to abbreviate piecewise as PW. And the derivative of the trig functions is what we'll start with, and honestly they're just things you have to memorize. There's 6 of them: the sine, cosine, and tangent, and their reciprocals. So d over dx of sine of x is equal to cosine of x. D over dx of cosine of x is equal to negative sine of x. And then the derivative d over dx of tangent of x is equal to secant squared of x. Alright, now they're reciprocals. D over dx of cosecant to negative cosecant of x times cotangent of x. D over dx of secant of x is equal to secant of x times tangent of x. And d over dx of cotangent of x is equal to negative cosecant of x times, oh wait, no. This was wrote wrong. It's just negative cosecant squared of x. So the derivative of cotangent of x is negative cosecant squared of x. I feel like I need to double check that because I had it wrote wrong and I made a note of it. Yes, that's right. Okay. So now, example. Given f of x equals x squared times cosine of x, find f prime of x. So I have x squared times cosine of x, so I have to use the product rule. So f prime of x will equal first times the derivative of the second. So if I look up here, what's the derivative of cosine of x? Negative sine of x. Plus the second times the derivative of the first. Derivative of x squared is 2x. And then we could simplify that using multiplication. This would be negative x squared sine of x. And we could write that as 2x cosine of x. So that is f prime of x. Number 2, same thing, find f prime of x of f of x equal to secant of x divided by 1 plus tangent of x. What rule am I going to do this time? Quotient. Anyone know how the quotient rule starts?
Second, second, the derivative.
Good. The bottom times the derivative of the top, or low d high. However, are y'all on a consensus of how you're going to say it? I try to say it how y'all all want to say it. So how are y'all saying it? You just know
I
it?
just know
times
f prime of x.
Okay. G of x times f, the derivative, g of x times f prime of x. Okay. So the bottom, 1 plus tangent of x, times, what's the derivative of secant of x? I can look back at the top. Secant of x times tangent of x. And then minus the top times the derivative of the bottom. I'm going to rewrite this down here. Should have done that to start with. So minus the top secant of x. What's the derivative of 1 plus tangent of x? Good. The derivative of 1 is 0. The derivative of tangent of x is secant squared of x. And so now all over the bottom squared. And then we can simplify the numerator. We can distribute secant of x, tangent of x to 1 plus tangent of x. So that gives us secant of x, tangent of x, plus secant of x times tangent squared of x. And then secant of x times secant squared of x would be what? all over 1 plus tangent of x squared. And we can leave it like that. Alright, now an absolute value one. Not an absolute value, piecewise. So example number 3, find f prom of x of f of x equal to negative 2x plus 3 for when x is less than 1, and x squared for when x is greater than or equal to 1. Alright, so this piecewise function I know at 1, I'm going to have to the left of 1 some linear function with a negative slope. And then at 1, I'm going to have, it's connected, so I'll have an open point there, and then it'll become x squared to the right. And so when we find the derivative of a piecewise function, we just find the derivative of the top and its interval, and the derivative of the second piece for its interval. So what's the slope for this linear piece? I can use my
-2.
I can use my constant and power rules. The derivative of negative 2x plus 3 is just negative 2. And so I have the derivative of negative 2 when x is less than 1. And then the derivative of x squared is 2x, so my f prime of x equals 2x when x is greater than or equal to 1. And now example 4, f of x equals the absolute value of x. So I know that function is at 0, 0, and makes a v. So absolute value functions can be wrote as piecewise functions with their two linear pieces. So absolute value functions, to take their derivatives, we rewrite them as linears. We rewrite them as piecewise functions, which are linear pieces. I could not get that out. So f of x will equal, we know the left side of 0 is negative x. So negative x for x less than 0. And the right side of 0 is positive x. And remember the thing on your interval where your piecewise function's connected? One of them has to be included, but you can't make both of them included because then it wouldn't be a function. And then now we can write the derivative. I know for when x is less than 0, what's my derivative? Negative 1. And then for when x is greater than or equal to 0, what's my derivative? Positive 1. So for when. But can I take the derivative at 0? No, because it's a sharp term. So I can't include 0 on the derivative. So this one, I could include 1 because that's not a sharp term. But for this function, I cannot include 0 because it makes a sharp term. So be careful on that. Can't take derivative of sharp term. So don't include 0. Okay, we will stop there with our notes today. So remember, in class tomorrow, all you're doing is working on assignments.